Okay. Hi, everybody. I hope you can hear me well.
I can hear you well.
Good. Could you please turn on your camera? As many as you could, as always, right? That's very good. The plan for today is to talk about hardware for machine learning system. So basically, if you remember this deep learning system stack, or in general machine learning system stack, it had several layers. At the top was basically the programming API that you were able to write your code, define the architecture of, for example, the neural network that you have, or some detail about the machine learning model that you want to define. Also some API for training, and several others that we already talked about. A layer below that was the system layer that you already talked. To some extent, this is mainly about the computational graph, right? How you can translate, this framework can translate the task that you define in your model and translate that to a computational model that can be efficiently deployed on the hardware, the layer below that. And today we are going to talk about this hardware layer, which is also very important to understand the detail, the connection. Obviously, you don't need to be expert in hardware, especially for those of you non-CS students. But we want to make a sense out of it, right? And not all CS students know a lot detail about hardware, but we want to make a sense out of it today, mainly emphasizing on the key problems, right? Understanding the key problems, and some of the exciting work that is going on these days, especially the connection between hardware, or basically hardware for machine learning systems. These are very exciting and kind of important area, at least at the moment in research, and soon in larger scale deployment. Before we go into the detail, do you have any question, as always, about anything you want to highlight? I hope you're doing well on the project side. Do you have any concern? Is any team has any concern? The latest that I know that most of you are in good shape. We had like one or two teams still struggling.
Professor, I have a question.
Yeah, go ahead.
So few of us they submitted the assignment. So, after, for example, after the due date or in the middle of the semester, if we found that okay, these kinds of things I could do in my first assignment. So because you know that our idea is sometimes some idea that didn't came to our mind. So
Right.
in the middle of the project, if we find some new idea, just by discussing with the other students, or by anyhow, so can we add these things in the first project? So
that's a very good question. That's a fantastic question. Thanks for asking. Yes, I highly encourage that. And probably we did not mention that specifically how you are going to do that. So my thought is that this is one way you could do this. You could create a tag or branch on your GitHub repo, about this assignment, I'm going to clarify it very precisely what exactly you need to do. For this assignment, when you submit it for the first time, right? Until the end, when you deliver everything, including task 2 and task 3, obviously you can update all of these, right? But I want you to have a specific branch or tag. I need to think about it, about this submission. About your grade, we are going to consider basically what you submitted at the end. So whatever update you could do, the only thing that I want you to do, because my approach is that I trust you guys. So basically, please don't try to copy from other groups and so on. About specifically this assignment, I trust you that you do your best and you do creative, original work for these assignments. But please, yeah, no cheating or copying from other groups. But I'm sure that you don't do that, right? But to be precise, we allow you to update these, and we only grade the whatever you deliver at the end regarding all of these tasks. We have these due dates specifically for you to make sure that you have some milestones in between, right? So you can see yourself the progress that you have made, and this will help you to focus on different tasks of different flavors, specifically as your TA Ying mentioned. Task 2 is relatively more difficult than task 1, but I'm happy that this tutorial helped you a lot to get this first task done, and this is good sign. Probably we need it at the beginning, but this is work in progress, right? So thanks for your feedback and highlighting it. I think about this tutorial as a hello world for this framework. So this is good that you were able to get things done. Any other concern or suggestion?
So when you say that the final graded version is the version at the end of the semester and we can continue to make updates, does that also mean we're not going to get any graded feedback until the end of the semester?
No, we are going to give you feedback, definitely. And that's why I want you to basically mark this because we are going to look at it now, right? But we'll send hopefully tonight the updated. We are updating the instruction. So the instruction has been updated. Ying updated it yesterday, and I'm going to finalize it tonight. I will send you once I'm done via Piazza. Any other questions?
Yes, Professor.
Yeah.
I would like to ask, our submission for my group, we submitted in our repository. We invited Ying as a contributor. Is that okay, or how do you want us to submit?
We updated the instruction. I agree that it was not super clear about every aspect. So I want to make sure that you know exactly how to do this, deliver this, right? Task 1. So again, make sure, so this thing that I mentioned, that we only grade the whatever you deliver at the end, this doesn't mean that you should not submit task 1. If you do not submit task deliverable, you will get 0. And I'm serious about that. So if you do not submit, if there is like serious problem with your submission, you will get 0. And whatever you deliver at the end. But if you submit and it is reasonable, we give you feedback, we want to help you and keep learning, we only give you grade about the last submission, right? But like you have this constraint, you have to submit for the deadline for each task at the specific time. And please, once we send out the final instruction, read them carefully again, and make sure that you understand every single detail. We repeated this many, many times, that if you have any question, you want to clarify, ask to clarify things, create an issue, whatever, right, and ask your question here. And we need to make sure, we need to know where we can find your repository, and it will be in detail mentioned in the instruction when I finalize it and send it out. Does it make sense?
Yes, it does. Thank you.
Very well. Any other question? Yeah, this is great. And yeah, and this, there are some also news about this Athena framework that you will hear soon at some point. One of these large companies decided to adopt this for the backend. So this is great that you're learning more detail about this framework for adversarial defense. That's great. Okay, so yes, hardware of machine learning. This is exciting. I showed you some different version of hardware. Let me show you, that might be useful. So like, for example, we have different, totally heterogeneous kind of hardware, right? So you have as a small kind of hardware as this one, which is super small. I showed you before. You have like a slightly bigger, this is for example from Google, TPU is slightly higher capacity, GPU and CPU, you have like bigger one, this is NVIDIA, this AGX Xavier, typically NVIDIA use this hardware, for example, for self-driving cars. This is the development kit, but we have the real kit that is used basically in self-driving cars in the lab. I don't have it at my house. We have like some other super small, smaller kind of hardware. One thing that like some other, like these are, for example, some communication module that I'm using for creating some, you know, some robots and stuff, and some hardware for doing machine learning. For example, I mentioned about this project that we have for blind people. So I'm assembling and putting together some of these. So the goal is to be as small as possible, because we want like attach it to glass. There are some smart glasses out there, but I'm trying to like develop something small so it is reasonable, so we can attach it to glass, so for enhancing the perception of blind people. So what I wanted to mention was that we have so many different hardware platforms, and especially these days, these heterogeneous hardware platforms appearing every week or every month, and the difference is that there, for example, macro architectures are essentially different. There are some differences in terms of obviously memory, compute, and the kind of capability that each of these expose, but essentially with respect to the principles and like the stuff that you need to know, this is what we want to talk about it and why it is these are important, right? We discussed about the trend in machine learning. We discussed previously that basically even neural network was out there many years ago, right? In 1950s, they were not deep. It was perceptron, right? In 1980s, we have convolutional networks for example, for identifying checks, the kind of famous LeNet architecture. It was not deep, but like it was a sort of convolutional neural network. And after right around 2000 time, due to appearance of large data sets like ImageNet and appearance of GPU, now this big revolution happened. As a result, the trend is that the trend is really simple. We have more data, right? As a result of more data, the models get bigger and bigger. They get deeper and deeper. Means that you need to train more weights. So this network, as a result of getting bigger or deeper, you have obviously more weights to incorporate in your training. And obviously for both training and inference, you need more compute, right? And make sure that you understand. And we want to, I want to somehow discuss about these differences between training and inference, because this is a bottleneck for both, right? And you already know some of the details, right? We discuss about training a lot for different type of models as well as inference. But now, as I mentioned, the plan for today is only talk about the problem. We want to understand the problem, what's going on. The goal is really simple. We want to run the network, the neural network faster. Basically, we want to get better performance. Or you can think about it as a throughput, right? You want to get more inference time per second, for example. Or in other words, so this is about running them faster, especially like, for example, when you deploy a neural network on some of these hardware, you want to, like in 1 minute, you want to run several hundred inference, right, prediction, or several thousand, depending on the power of this. So you want to increase the throughput for a specific hardware. But on the other aspect, you also want them to run them very efficiently. Why that is important? And the way how you can think about it, you should separate training from inference. For training, you could assume that you have a server in a data center, right? It has a GPU. You can even train a large network. So obviously you can, but you need to pay for the GPU server. And we discuss about it, what it means, because it is costly to run a data center. So you need to do the training very efficiently, but you don't have the concern that my hardware is connected to a battery stuff. But for inference, once you have the model trained, you want to take it and deploy it in some of these hardware, these embedded hardware. And typically these embedded hardware are connected to a battery. So you need to run your model very efficiently. For example, if you use it in a robot, you want to do many different missions with this robot, not basically recharging it again and again. Or if you wanted to use it on your mobile or watch, you don't want to run out of battery soon. So it is important to get energy efficiency, right? And energy efficiency means that inference per joules. Joules is the unit for energy, right? So if you're familiar, this is the formula that you have, right? What is joules per second? You might have heard about what more, depending on the context you're familiar with. But essentially, you want to think about energy as inference per joules. And also, you can define in terms of cost as well, inference per second per dollar. You can think about that as well. So for inference, what's happening, you just the neural network in a forward path. For training, we discussed about it. You run forward path, then you need to run backward for propagating the gradient. Basically, you need to calculate the gradient of the loss with respect to weight. So once you have done the forward calculation, you calculated the loss, you need to calculate this guy, right, through the backward propagation. And then in the last stage, you want to update the parameters and do the same, right? So you have this loop of these three essential operations during the training. So that's the difference between inference and the training. Is that clear? Do you have any question about this? We discussed about neural network extensively, and this is the deep, basically fully connected neural network, right? So we discussed about this, so you know the detail. Essential operation that we have in DNNs, deep neural networks. And again, contrast deep neural network. We'll discuss in detail the difference between, we already discussed, but in terms of hardware, the kind of concern you should consider in both fully connected network as well as convolutional neural network, because the kind of operations are essentially different. In DNNs, if you remember, we had a bunch of input units. So each of these were units and bunch of output units for each 2 consecutive layers. And these were essentially your weights. And you had so many of these weights, right? So the if you want to count the number of weights, how do you calculate it? If you have, for example, let's imagine that you have X number of units in your input and Y number of units in your output. How many weights you have?
Just X times Y?
X times Y.
Yeah, exactly. So it's X times y. And imagine in like normal neural network for image processing or whatever, if you have like 4,000 units in the input and 4,000 unit in the output, how many weights you have? Is 16 million, right? So is a large matrix that you have as a result. And this is only related to this particular part of the network, okay? So these, you have a weight matrix, which is super large, like 16 million parameters inside it. And you have your activation, and this is like your input activation, okay? In order to calculate your output activation, you do this matrix to vector multiplication, and this is a very expensive operation, isn't it? You have a large matrix, 16 million, right? And you need to do the dot product, right? So you have this and you have this, you do the dot product to create this, the first one, right? So essentially you're doing 16 million kind of multiplication, which is a lot, right? So this is very, very expensive, but more importantly, if you think about it, where are these weights located? Like essentially, when you do this operation, where are these weights located?
In RAM.
In RAM, exactly. They are located in RAM, and you need to retrieve them from RAM, right? So they are in your DRAM, and like retrieving weights from RAM is expensive operation. It's not as cheap, right? Especially in terms of energy consumption is an expensive task to basically retrieve these weights from RAM. But more importantly, if you think about this carefully, when you move to the next layer, what happens?
I mean, you need a new set of weights, or you need the next set of weights.
Exactly, you need next set of weights, and this guy was totally different from this guy, right? So these weights were different from these weights. So basically, for the next layer, you need to retrieve these weights again, which are totally different, right? So you need to, when you move from one layer to the other, like from here to here, you need to again retrieve like 16 million or more, even, because this is bigger typically, weights from your RAM again, which totally different, right? And again, doing this expensive dense multiplication matrix to vector multiplication to generate your next layer activation layer. Okay, so you are really doing very inefficient operation with that sense. And you need to basically do this until the end, until you generate your output, basically your losses, and you need to do the same sort of operation we discussed about it for doing backward, right? Essentially, you need to go back, calculate this guy based on what you have here, right? So you need to do similar operation for doing the backward during your training, right? So obviously during your inference on top of these dense network, you don't need to go backward, right? You only go forward, but during training, you have the same kind of expensive operation to do. And the benefit or the difference, or how can I say, the what is the word for that? The kind of opportunity that you have in training that you do not have in inference is that you can batch your input, right? So in inference, you cannot batch your input because the input come at one, right? Like when you use your camera, you see one thing, right? And then you move on to something else, right? So you cannot move toward during time to batch these examples, right? It doesn't make sense. So you only do this one image at a time, but during training, you have your training set, and we know that like we could do a stochastic gradient descent. We have the mathematics behind this, right? So at least maths is helpful here. So we can batch them to make it more efficient. Why it is more efficient? Why do you think it's batching is more efficient?
You're calculating a gradient less times, I guess.
Calculating gradient less time, what do you mean?
Well, and when you're batching, I mean, you're calculating the gradient for the entire batch, like in some way at the same time, unless I'm misunderstanding.
Yes, yes, but what else you get? You're referring to this guy, right? So you calculate for all of here is K is the batch, your batch size, right? But what else you get here as a result of so it's obvious, right? So you load these weights for all of these batches, all of these examples, right? So you don't need to basically access your memory for every single images that you have because you batch them and you have calculated all of these activation at once, right? So you retrieve these weights once and you reuse it across all of your batch, right? So that's the kind of benefit that that you get as a result, which is super cool, isn't it? Even though this is expensive, but and that's why batching makes sense. That's really the key reason batching become popular and was needed. It was mainly for efficiency purposes rather than the kind of algorithmic purposes, because from the algorithmic purposes, yeah, you get some property, but essentially you are messing around with your, because like you get better, more accurate signal per image, right? Even though in math works with stochastic gradient descent because you batch them, but essentially you get every calculation you do with a batch, you somehow make an average across all of the example inside your batch. So it's more noisier, I would say. But at the end it converges because you do several iterations, but essential for each iteration is more noisier, the kind of calculation you do, but essentially this is for the purpose of computation. But if you think about this, and we discussed about the sparsity before, if you remember, in the context of convolutional neural network.
Just a moment. I couldn't find any matches in your photos library.
Stop, Siri.
Here are some images from the web.
So these activation units, basically, mostly they are 0. Can you remember why they are mostly 0? Can anyone recall? Are you guys following?
They're mostly 0 because the weights are sparse, as if they're not connected.
Why they are sparse? Why the weights are sparse?
I remember you did some 0 padding on the outsides of your data to keep the dimensionality the same so that you could continue to do pooling and add layers.
That was for convolution, right? That was for convolutional network. This is for fully connected. But essentially, if you think about it, right? So think about activation, right? So essentially, like what you said, is true, that the weights are sparse. Actually, both of them are sparse, and let's think about it, why they are sparse. So the output, this is for the backward, but like think about like these 2 layers, right? Or maybe let's go to this, right? If you remember, once we do this multiplication to generate the output, to generate this activation, we discuss about nonlinearity, right? For example, you need to apply like ReLU, right? How was ReLU? Was like this, right? So typically most of them will end up to, after passing through this ReLU transformation, end up to being 0. And only the positive one stay the same. Okay, the negative values will become 0. So many of these activations that you get after passing through this nonlinearity became 0. So obviously you have this vector, you will see a lot of 0 in there. Okay. But essentially, as a result of training, also if you look at this empirically, these weights matrix, we discussed that when it came for convolutional neural network, it is a lot of 0 in there as well. As a result of the mathematics, this matrix multiplication, essentially, right? And the back propagation that happens, and the weight update that happen, a lot of these weights are either 0 or very, very small, close to 0. And typically, if you plot the distribution, they're mostly centered around 0. So if you think about like the weights, if this is, for example, 0, these are negative, positive, they're mostly like this, the weights, the value of the weight. So basically you have a lot of weights inside this matrix which are centered around 0. And typically we will discuss about this when it comes to pruning. You can prune a lot of these small values to make this a law sparser, right? So you have matrix that a lot of its value are small, and like you get rid of them by making them 0. You don't need to be worried about that, right? So that's a thing that happens for model pruning, which we will discuss probably after this lecture, once we are done with the hardware, because it is relevant. So you prune them away, make them 0, so you get a lot more efficiency, right? So basically now you could do a sparse matrix to a sparse vector multiplication, right? And you know that these sparse operations are a lot more efficient. So this is the efficiency that that you get as a result of if you do both pruning and this is by default is sparse, then you get a much more efficiency in terms of operation that you need to do for this calculation, even for fully this dense network. Do you have any question about this? Everything is clear? But like one thing you need to know, and maybe you want to think about it. So imagine that you have different images, right? Different input. Since every time a new image comes, right? After you pass it through the nonlinearity, for each of these output, the location of 0 would be different, right? So for one image, right, maybe the zeros are here, right? For another image, the zeros are somewhere else, right? Because of the way that the information passed through, right? It came from here, right? Passed through here. So you get the sense, right? The places, the location that these zeros are located are different. Or for these weights, once you have the network trained, they are fixed, right? So you know exactly where are these 0, right? After you prune the way, prune the small values. So this operation became a little bit tricky, how to do that efficiently, because for different image, the location of these zeros would be different, but like the zeros here, you know exactly where they are, right? But somehow this operation as a result become tricky if you want to ensure that like you get through a sparse to a sparse multiplication for all of your data, right? And that's why it's not as easy, but again, like this is a lot more efficient when comparing it with like non-sparse matrix to vector multiplication. So difference in terms of regularity where these zeros are. And if you think about the whole architecture, we discuss about, this is about convolutional neural network, right? So now we discuss about CNNs. So we have an input, right? And we have some kernels that moves to your inputs and generate these feature maps or channels, right? So you move this in your input, you generate several feature maps, and then you do the same here. You have your kernels move here to generate these feature maps for the next layer. And you do this many, many times, right? Throughout different layers. And the trend that you see here, your feature maps, we discussed about this in previous lecture, right? This is a different perspective, but like the same, right? These feature maps are in terms of size. Look at the size, right? This is your input, slightly smaller, right? And getting a smaller throughout. Okay, getting a smaller throughout in terms of size, but in terms of numbers, you have more of these feature maps when you go to deeper part of the network, right? And these feature maps again essentially are associated to the features that the network learn as a result of training, right? And then also you have this subsampling that we discussed, like about pooling stuff that you do in convolutional neural network to get this a smaller size of network, and these invariances that we talk about, okay? And once you have this final layer, we discussed that last thing you want to do is the classification, the fully connected part, right? The FC part. So here you have fully connected network in order to generate your outputs. And these outputs are basically the classes that you have. Like in this case, for example, this is, you have 10 outputs, right? These are the probability of the label after you pass it through the sigmoid function. Or if you consider it this, it might be your logits as well. Then you need to do sigmoid to calculate the probabilities. Okay, so this is the overall architecture of convolutional neural network. We extensively talked about it, about the detailed mathematics and operation. But let's think about the hardware aspect as well, how it looks like in terms of efficiency of calculation, right? So here, this is your input map, right? This is, for example, here, this is output map. You have these guys, these are your kernels that run through this input map, right? And you have multiple input maps, right? And you have multiple output maps as well as a result. So this kernel, you move it along this input, and in order to generate one of these outputs, right? So essentially, you have a matrix to vector multiplication, right? Why this is efficient? In what aspect, and not efficient in some aspect? Can you make a sense out of it?
So the kernels are a whole lot smaller as far as the memory impact. They have far less weights for an entire layer. So you've got less to load from RAM right there.
Exactly. Brilliant. What else?
I mean, as far as accuracy goes, I'm guessing you just don't have the capability of learning nearly as much, as complex a function between the two. Although I don't know if that's what you're seeking as far as, are you looking for more hardware?
No, more hardware, right, exactly, more hardware. So basically, this happens as a result of parameter sharing, right? So you have very small kernel. So your kernel is essentially a small, right? And this needs to go through all of this input map. to generate this output map, right? But like this is positive that these are small, right? So these guys are small. Right. So, but what is the expensive part?
It would have to keep track of all the feature maps in memory during runtime.
Yes, that is true. You have to keep track of these during runtime, right? So you need to store them in RAM. But again, there are not 16 million, right? So they are small, right? Like 32 by 32, okay? I mean, relatively small. Not many cells there are inside each feature map, and as you move here, they are getting smaller, right? But you have many of them. But again, in terms of like, it's nowhere near like 16 million, right? In deeper network, yes, like as a result of getting deeper and deeper, like convolutional network also have like so many weights relatively, but a lot better than fully connected. The thing is that here for convolution, you need to do a lot of arithmetic operations, right? In terms of memory, they are small, but you need to run this kernel like throughout, right? So you need to do a lot of arithmetic operation, meaning that multiplication and addition, right? And if you think about this, so in order to generate this output map, is bx y j, you need to run a 60 loop, right? So for each output map j, for each input map k, right? Essentially, these last indices indicate the slice, right? And for each pixel xy, right? For each kernel element uv, right? Kernel element, you need to do this operation, okay? And add them up for calculating this x, y, j, is essentially this guy, right? So you do this multiplication in order to generate this, and so you have to do many arithmetic operation, right? Even though this multiplication is really inexpensive, right? But you need to have to do many of them, right? Essentially, this is by itself very inexpensive because these are small. But you need to run through the whole thing, and you have like many of these channels, right? That you need to run this operation. Does it make sense? So comparing with the fully connected network were bound from large size of weights, right? And like memory, here is you have more calculation, arithmetic calculation, right? You're not bounded by memory. But again, if you think like you also need to do fully connected operation at the end, so like you have some restrictions there as well, but it's a lot more efficient. So because these weights are shared essentially. So these are relatively much more efficient than fully connected networks. And if you think about some other type of model like recurrent neural networks, here essentially RNNs are like dense network. Essentially, you have fully connected operations like we had for DNNs. Here, these inputs are connected to your output, but in addition to this, once you calculate these output, you run it through these guys. These are like your memory cell in your recurrent network, and you need to again feed it back to your output in order to generate the next activation. So this is more or less like fully connected networks. If you want to compare it, and RNN, you know that they're used for example, for a speech. They are expensive kind of operations.
And the idea there for speech you were mentioning, like, is that it maintains some kind of memory of like past input, right?
Exactly. So these memory cells remember stuff, especially if you have some regularities like a speech, right? But like we haven't talked about the RNNs yet, but if we get time, maybe we have a lecture about it, but let's see. So in CNN, you have some other operation as well. You have pooling, right? We discussed about that. This is like you have a stuff, right? And your activation, you want to take the max, if this is max pooling, in order to do this subsampling. You have ReLU, which is relatively inexpensive, right? It is very inexpensive operation in terms of calculation that it does, right? Everything here, 0, the rest would stay the same. In terms of implementation, is so simple. But this guy, like, you need to also update the weights throughout training if you're doing the training. And in CNNs, still you might have, in deep CNNs, you might have a large set of weights that you need to update, and you need to keep them obviously in memory. You somehow have this concern, especially if you want to do that for a large batch, and that's why sometimes during training you're bounded on the size of batch, right? You want to do, especially these are happening in your DRAM, and like you have limited size of DRAM there. So you cannot, and that's why you cannot do large size batches. You're typically limited by the amount of memory that you have. The batch size during training is limited to the amount of memory that you have, right? Does it make sense? If you have large set of weights, right, for large byte sizes, then this becomes really large. And the whole pipeline, if you think about this, and if this is, for example, training, like you store your images somewhere in your disk, you need to load them up. Typically, they're in some compressed format like JPEG. You need to decompress it, and then once you have the raw image, you do your calculation with DNN and generate your output. And like each of these operations are like different essentially. Like this is disk access, right? So you have obviously a slow operation there. Decompress, you need to make it efficient, right, in order to have the whole pipeline very efficiently. Like if you make this DNN guy very efficient, and these are slow, then you don't get end-to-end performance, right? So if you make one component very efficient, other components are not efficient, then the end-to-end doesn't change. So there are some like opportunity to, for example, make the compression algorithms more efficient, more performant, and also disk operation as well. And that's why the whole end-to-end, and this is very much related to this course, machine learning system. And this stuff happen like in practice. I mentioned that many times, right? In company like Google, when they have end-to-end pipeline, like this is not only about like making this DNN, one DNN guy more efficient. This is about making the whole pipeline efficient. And hopefully throughout this course, you have already got a sense of what are those challenges, why they are important, and what are the possible solutions and how you can approach it, right? And that's why this course is very important for you guys. Hopefully you learn something throughout this course, and there are more coming, right? And hopefully you enjoyed the course so far. So to summarize, basically you have these different models from fully connected, convolutional, RNNs. There are concerns in terms of training and inference, right? Batch size stuff, we need to optimize it. We have some basic operation, these matrix to vector operation. Maybe we can do a sparse operation for convolution, like we discussed about like memory versus arithmetic kind of operations and the other stuff. So let's stop here. Do you have any question? Great. So good luck with your project, and see you on Thursday. Thanks.
Okay. Thanks, Professor.
Thank you.